გამარჯობა. ესეც ასე. სალამი ხალხებო, მოდი აბა აქ დაშვება ყველას. ვინც შემოსულები ხართ და დავიწყოთ დღევანდელი შეხვედრა. შევხედოთ აბა.
მოგესალმებით მოსწავლეებო.
გაგიმარჯოთ. მითშიც სალამი ხალხებო, მოდი აბა აქ დაშვება ყველას. კაი, ხმა გავიდა. ეს არ გვინდა. კიდე რა გვინდა? კვანტი. ესეც ასე. ეხლა გვინდა კამერის გაშვება. აი მეც გამოჩნდი. და დღევანდელ დღესთან დაკავშირებით, ესე იგი რა იდეები გვაქვს. დღეს როგორც გითხარით, ხო. დღეს აგრეთვე არის დედაენის დღე. 14 აპრილია და ორივე დღეს ერთად გილოცავთ, ასე ვთქვათ. მოდი დავიწყებ იმ სიტუაციით, რომ დღეს რაც შეეხება კვანტურ კომპიუტერებზე თემას. დღეს გვექნება IBM-ის კვანტურ ლაბორატორიაში გასეირნება, ექსკურსია, ასე ვთქვათ. შემდეგ შემოგთავაზებთ სახელმძღვანელოებს, ზუსტად არ მახსოვს თანმიმდევრობა, ჩამოწერა ხო, Google-ის ლაბორატორიას დაგათვალიერებთ აგრეთვე. შემდეგ შემოგთავაზებთ წიგნებს, რა წიგნებით შეიძლება კვანტური კომპიუტერის პროგრამირების სწავლა და აგრეთვე შემოგთავაზებთ კოლეჯებს, ამერიკულ კოლეჯებს, სადაც შესაძლებელი არის სწავლის გაგრძელება, პლუს ამას გარდა შემოგთავაზებთ უფასო პროექტს, ქისკითის უფასო პროექტზე მოგიყვებით და გეტყვით, როგორ შეიძლება ამ პროექტში კვანტური კომპიუტერის პროგრამირება. იგივე პროექტი შესაძლებელია, სრულიად თავისუფლად შესაძლებელია თქვენ საკლასო ოთახებში მოეწყოს. ანუ ერთადერთი გჭირდება, ერთადერთი რაც ჩვენ გჭირდება, ეს არის მაღალი სიჩქარის კი არა ინტერნეტი, რომელსაც თუნდაც Facebook-ზე შევდივართ. რამე განსაკუთრებული სიჩქარის ინტერნეტი და განსაკუთრებული პირობები ამ საიტს არ გჭირდება. უბრალოდ ერთი პრობლემა წინაზე რაც გითხარით, ეს არის რომ IBM-ი და საქართველო შარშანდელი წლიდან მთლად ვერ მეგობრობენ და ჩვენ ზოგიერთი პროგრამიდან გამოთიშულები ვართ, თუმცა ჩვენს ორგანიზაციას აქვს ხელშეკრულებები და ეს ხელშეკრულებები ჯერჯერობით არის მოქმედი, რაც ნიშნავს იმას, რომ ჩვენ შეგვიძლია ვისარგებლოთ იმ სიკეთეებით, რასაც IBM-ი გვთავაზობს უფასოდ. და ეს ნამდვილად არის ძალიან მნიშვნელოვანი სიკეთეები კვანტური კომპიუტერის, თუნდაც კვანტური კომპიუტერის პროგრამირების კუთხით. და ნუ რა ვიცი. მოკლედ დავიწყოთ დიდად არ მოგაწყენთ. ერთი რამ მინდა გითხრათ, რომ გურამი და ანასტასია არიან შემოსულები მითში ვიდეოს ხმა არ იქნება, ამიტომ ჯობია რომ ისევ YouTube-ზე ნახოთ და გავაგრძელოთ შეხვედრა და YouTube-ი გამოვიყენოთ. მითი გამოვიყენოთ იმისთვის, რომ თუ რამე კითხვები გექნებათ, შემდეგ უკვე შეგეძლებათ ამ კითხვების დასმა.
დას YouTube-ზე რომ ტელეფონით შემოვიდე და მითშიც ვიყო.
კი ბატონო. როგორც გაგიხარდებათ, ვიდეოც არ იქნება, ამიტომ ჯობია რომ ისე მე გავამზადებ ახლა აქეთ ამ მხარეს ხო, ჩვენი კურსისთვის აი 25-ში გქონდა ჩართვა, შეიძლება თქვენთან იმაზე რა არის, რა ქვია, ვინც ჩვენთან ერთად გადის IBM-ის და MIT-ის კვანტური კომპიუტერის პროგრამირების კურსს, გქონდა ლაბორატორიიდან ჩართვა.
So I'm just gonna walk next door.
Cora, while you're walking, do you think you might have time to answer a question or two from the Q&A, or are you close?
Oh, I'm already at the lab. But
Okay, never mind. We can save that for later. Keep those questions coming though, folks.
okay, so it's really loud in here, so hopefully you can still hear me. I'll try to talk loud too. I don't know if you can hear that sound that's going on in the background, but that's the pulse tube, because our qubits not only have to be cold.
და მოკლედ ამ ვიდეოს ჩართვა დღეს გადავწყვეტე რომ ეს ვიდეო არ ჩამერთო, მე თუმეტეს რომ 25-ში ეს ღონისძიება უკვე გქონდა ჩვენ და შეიძლება რომელიმე თქვენთაგანი უსმენდა კიდეც ამ შეხვედრას. პლუს ამას გარდა მე რაღაც ინტერნეტზე იყო პრობლემა, გაეჭედა რამდენადაც ხვდები ამ გოგონას და მოდი ახლა ჩვენ ნახოთ, დავიწყოთ შეხვედრა, დღევანდელი შეხვედრა დავიწყოთ IBM-ის ტურით. და შემდეგ უკვე სხვა დანარჩენი.
Hi everyone, my name is Eric Lucero. I'm pleased to have you here at the Quantum AI campus. I'm going to walk you around, show you a bit about not only the history of how we got here, show you a little bit more about the space and the lab and where we're headed. So I'd love to start with our Sycamore quantum processors. Behind this piece of metal right here, on this circuit board and all these connectors that we have, is the actual quantum processor. This system gets mounted into our cryostat, and that system we're going to see in full scale in just a moment inside the lab. So it's also a pleasure to have you here for all the reasons we can show some of the collaborations that we've had from our 9-qubit systems that have now scaled up to, say, beyond 54. Here's a nice example of one of our systems that we had that was 22 qubits. And it's really cool because all these will be put together in the lab that you're about to see. So I'm going to take you there. So come with me. Now I'm going to show you where we take those Sycamore processors that I showed you earlier and install them into the cryostat. So we're going to walk over to one of my favorite systems here. This little cryostat is what we use to cool those systems down to really a couple orders of magnitude colder than space. Basically, each one of these metal stages that you see here, from this edge all the way down, kind of in this layer cake, the very bottom of that is what we call the mixing chamber. At that point there is where we mount the quantum processor, that Sycamore system that I showed you earlier, and it thermalizes to that plate. That plate gets to 10 millikelvin. That's really cold. That's some of the coldest places in the universe. That's 2 orders of magnitude colder than, like, between 2 galaxies. All of that system runs all the way up the top where we have wires that come out. You can see over here on our control system, those are custom control electronics that our team, engineers here at Google, have done and designed specifically to control the quantum processor inside. I like to think of them as a music player, playing music to the qubits. There's some analog pulses that come down, and that musical score gets played through those wires all the way down to those qubits. There's a lot of different skill sets all over the world that these people are coming from to join the team and think about what is a quantum computer actually going to serve everyone, and how do we do that responsibly for the world and make this a tool for humanity. All right, so now I'm going to tell you a little bit more about what this space is going to look like as we scale in the future. Today, we are here right now at this point where we've just gotten past the beyond classical experiment. And we're headed towards these next milestones to build an error-corrected logical qubit, and finally, to an error-corrected quantum computer. Now this space will grow, and we've really designed it to be the kind of place where we can land a number of these milestones along the way. Each one of these cryostats are systems that our team has spent many, many hours in design and customizations to make these some of the most powerful quantum computers in the world. We can do the impossible. And we look at quantum computing, it's something that we look at as maybe it's a 10-year investment. At the other end of that will be this tool for humanity. And I think it's an important part of that style of creativity that is not just a scientist's creativity or just an artist, it's actually kind of that combination of both that gives us the ability to be inventing the future. So it's been a pleasure to share with you all this space. I can't wait to show it to you in person and to see this place come together for an error-corrected logical qubit. Until then, take care. I'll see you all later.
Who was it that said, if you
სიგამრის კომპიუტერთან დაკავშირებით, პროცესორთან დაკავშირებით, უბრალოდ 2019 წლის სტატია არის აი დათოს ბლოგზე გამოქვეყნებული და ნუ რამდენიმე პატარა დეტალს შეგიძლიათ გაეცნოთ აქაც. საკმაოდ ისეთი სიგამრი არის ჭადრის ხეს ნიშნავს, რამდენადაც მახსოვს და Google-ის ეს ხო, აქ კიდე ერთ პატარა ნიუანსი იყო, რომ Google-მა როცა ეს პროექტი იმას აქნა რა ქვია, გამოაცხადა, თქვა რომ ჩვენო არაჩვეულებრივი ძალიან დიდი პრობლემები გადაწყვეტეთო და მე IBM-ის სპეციალისტების ის იყო რა ქვია გამოხმაურება, რომ არიქათ თქვენ კი იძახით, რომ ეს რაღაც გლობალური და დიდი პრობლემა არის, თუმცა გეკითხათ ჩვენთვისო და ჩვენ ძალიან მარტივად ამოხსნიდით მაგ გამოცანებს. აქედან გამომდინარე მე კიდევ ერთხელ ვამბობ, რომ IBM-ი გაცილებით მაგარი და კაი ტიპები არიან IBM-ის ტიპები. და ეხლა შემოგთავაზებთ უკვე ჩართვას IBM-ის ლაბიდან. რეკლამები.
Hi, my name is Olivia Lanes, and I'm one of the scientists and education leads working here at IBM Quantum. And today I want to welcome you to one of our labs and quantum data centers. IBM Quantum has the largest number of quantum processors available through the cloud, and this is where we house some of them right here. So I'm going to walk you through the lab today, and I'm going to show you some of the room temperature and cryogenic equipment and all of the machinery that goes into keeping these devices and these machines cold. So the most important piece of equipment in this room is the dilution refrigerator, which is this big cylinder here. And this basically works as a Russian nesting doll. If you've ever seen those toys, it's basically a can and a can and a can and a can. And that works the exact same way. The outer can here is obviously at room temperature, and then there are 4 other cans on the inside which get progressively colder and work to keep the thermal isolation at that stage of the fridge. The inner can, which hosts the IBM Quantum processor and lives here at the very bottom, is an insanely cold temperature of about 15 millikelvin, and every other can basically is progressively warmer than that. And there are also stages of the fridge as well, where the top part is at room temperature, and then again, the bottom part, which hosts the processor and the qubits themselves, lives here at the very bottom. So how do we get signal from the very bottom out to the rest of the world? Well, we basically have cables that run to the bottom of the fridge here, and then all the way back up to the top of the fridge into these room temperature amplifiers. And then those room temperature amplifiers make the signal bigger, and it travels through these blue cables into our room temperature control electronics over here, which digitize the signal and turn that waveform into something that is able to be processed and understood by our computers and our laptops. And one thing you'll probably notice is the sound. It's very, very loud in here because we have multiple dilution refrigerators all turned on and working at the same time. That's a compressor, that ch-ch-ch-ch noise. That's a compressor pump, which basically is pumping on these fridges at all time and keeps them at that insanely cold temperature. So back here you can also see a whole lot of more pumps and compressors that are working to keep the fridge and the flow of air and the cryogens static and working at all times. And if you come over here a little bit more, you can see we have a drawer of liquid nitrogen, which is the first cryogen that we use in the cryostat in order to cool it down to 15 millikelvin. The other important one is liquid helium, but you can't really see that. We keep it inside the dilution unit. But we need to make sure that this drawer of liquid nitrogen is full at all times. We have a little scale here to make sure that we can weigh it and see how much nitrogen is left in the drawer, and it never goes empty, because if we don't have enough nitrogen left in the drawer, then things start to warm up on us. And this is the control panel, which basically controls all of the valves and the turbo pumps that are working inside the fridge and outside the fridge. You can control them and turn them on or open them by basically just pressing these buttons. The blue color means these valves are open, and the gray color means these ones are still closed. So you can control that. Like I said, it's just a button with the press of a button. And then the laptop here is also an interface for all of the cryogenic equipment in the dilution refrigerator as well. You can log on and basically press one button that says full cool down or one button that says full warm up, and then you can basically cool down your device and warm it back up in 2 presses, 2 clicks on a computer. So it's really pretty simple. Like I said, this is more room temperature control boxes that digitize the signal. These cables carry the signal into more room temperature amplifiers that you can see here. Just makes the signal bigger so the computers can see the quantum signal above the noise floor. This is a hemp box which controls all of the cryogenic amplifiers inside the fridge that live at around 4 Kelvin. These are network analyzers, and these are current signals which send current or voltage into the fridge to control some of the amplifiers or other cryogenic components inside the dilution refrigerator. One other thing I want to show you in this lab is this device over here, which is a VNA, or a vector network analyzer. And this is a device that basically can tell us the frequency and the phase of the signal that we're sending into our qubits. And we like to use this as a first check in the lab when we're trying to see whether a new chip that we've made has all of the qubits at the right frequency or not. So come with us. We're going to go upstairs now because, like I said, all of these solution refrigerators are turned on and they're all working, which means you can't really see anything interesting inside of them. But we have our model upstairs, which is turned off, and I'm going to explain what you can actually see inside the dilution refrigerator in just a minute.
Уважаемые руководители и владельцы компаний, вы ищете квалифицированного маркетолога, способного регулярно перевыполнять.
So here we have our model dilution refrigerator, which is obviously not turned on at the moment. Because when the fridge is actually running, you can't see any of the internal parts or any of the cool things. But now that it is turned off, you can really see all of the different cryogenic components inside the fridge. We can start with the chip down here. So this chip, this quantum computer, has 16 qubits, and all of these cables here on the bottom and the top basically plug into the sides of the chip, which is wire bonded to the sides of the packaging. And then these cables carry the microwave signal to the isolators and amplifiers that are also kept at this same plate here. And then those carry the microwave signal back up to room temperature. So every individual stage of the dilution refrigerator is at a different temperature, just like the cans that I was showing you in the other lab. That connects right here. That's the room temperature part of the fridge, and that's the most outer shield. And then inside on every single plate, that has its own shield, which would attach from the bottom and get screwed on here. And every single shield is held at a progressively colder temperature. Starting out here, which is the one that we saw in the lab, and you could touch, obviously, that was at room temperature, down all the way to the mixing chamber plate, which is about 15 millikelvin. And that would be that gold shiny one that we saw in the lab as well. That is the lowest part of the fridge. And it's sort of like I I said in the lab, like a Russian nesting doll where every single can is just within another can. And that's to keep it basically thermally isolated from the environment. So once these cables go back up to this stage, they get carried all the way back to the top here. And one of the most common questions we get are, why do all of the cables have this little loop on them? And it's basically because when you cool down the fridge and then you warm it up multiple times, over a few cycles of doing this, these cables, because of the expanding and shrinking of the metal due to the thermal temperature of the environment, can get very brittle, and the cables can break if they don't have a little bit of give to them. This is the dilution unit, the mixing chamber itself, which is responsible for the cooling of the mixing chamber plate, which is the lowest plate of the fridge, like I said, 15 millikelvin, which is colder than outer space. And then this plate basically has the first two cryo pumps that are responsible for bringing it down to a reasonable temperature before the dilution unit pumps on it and introduces more cryogens to bring it down to an even colder temperature. Other things to note up here, you'll see a lot of copper wiring. That's because copper has really good thermal properties and is really good at basically helping to keep all of the parts that should be cold. These parts right here are just to connect the plates to one another. These are for magnets. If you had any magnet that you wanted to introduce into your experiment, you would plug those in here. And I think that's basically it, yeah. So the important things to note are the actual cooling parts of the fridge. That's what these parts are for. And then the parts that actually carry the signal to the processor are the ones that go in the middle, straight down through here, and then the signal leaves coming out the other side, and then those cables basically are distributed to all of these amplifiers and isolators. These basically direct just the flow of traffic, the flow of signal, to make sure that it goes back up the direction that we want it to, and not backwards into the quantum chip, where it can interfere with the qubits and cause noise. And like I said, all of these cables on the outside would carry the signal back up to room temperature, and there would typically be a bunch of cables, although this is just a demonstration fridge, so it doesn't have those cables, on the top of the fridge that would then take that signal and put it back into those room temperature boxes that you saw in the big rack next to the fridges that we looked at in the lab. Thanks for coming on the tour with us and sticking around. If you have any other questions about what you saw here on the tour, please feel free to leave it in the comments, and we'll see you next time.
ეხლა კი რამდენიმე სიტყვით მინდა მოგიყვეთ ძალიან საინტერესო პროექტის შესახებ. ამ პროექტს ქვია KISS-KIT-ი. ეს არის IBM-ის პროექტი. მოდი აბა გავუშვათ პრეზენტაცია. ესე. ხო, KISS-KIT-ი ეს არის ღია კოდის SDK კვანტურ კომპიუტერებთან მუშაობის და წარმოადგენს კვანტურ კომპიუტერებთან მუშაობის ინსტრუმენტს. წინა შეხვედრაზე მე პრეზენტაცია განახეთ, სადაც ნაჩვენები იყო თუ როგორ შეიძლებოდა თქვენს საკლასო ოთახში შემოიტანოთ კვანტური კომპიუტერის პროგრამირება, ანუ მოსწავლეებს როგორ შეიძლება ასწავლოთ კვანტური კომპიუტერის პროგრამირება და როგორ შეიძლება გამოიყენოთ ეს ყველაფერი საკლასო ოთახში. და გულისხმობდით ერთ-ერთი კომპონენტი, ერთ-ერთი ინსტრუმენტი, სულ თავისუფლად შეიძლება იყოს აი ეს KISS-KIT-ის ვებგვერდი. მოდი მე ახლა ვეცდები გვერდი განახოთ. გადავიდეთ. ძალიან ლამაზი გვერდი აქვთ. და შემდეგ უკვე იმაზე განახებთ, ინსტრუმენტებს განახებთ ამ ყველაფერს. ანიმაციით განახებთ უბრალოდ ამ ყველაფერს. ესე. KISS-KIT.org არის საიტი. და გადავიდეთ ამ გვერდზე. დაგვირდით. ეს არის IBM-ის გვერდი არის რა თქმა უნდა. აქვე არის მოთავსებული, აქ API-ც არსებობს ამისი, ანუ თქვენს ვებ პროექტებში ან მოსწავლეებს შეუძლიათ ჩააშენონ. API არის სხვა პროგრამული ესე ტექნოლოგია არის ზოგადად ეს ტოკენის გამოყენება ნიშნავს სხვა პროგრამული სხვის მიერ დაწერილი პროგრამების გამოყენება, როგორც არის შესაძლებელი თქვენს ვებ გვერდზე, ნუ აპლიკაციაში. ეს აპლიკაცია რა თქმა უნდა არ იქნება ვერ იმუშავებს ინტერნეტის გარეშე და ასე შემდეგ. აი ვინც Python-ში ერკვევა, ადვილად მოხდება ამ ყველაფერს. ხო, რაც შეეხება ფასიანია თუ უფასო არის და როგორ ხდება, რამდენიმე სიტყვით ამასაც გეტყვით. ღია კოდზე დაფუძნებული პროგრამული უზრუნველყოფა არის. ეს ნიშნავს იმას, რომ ამისი კოდები რა კოდებით იქნება გამოყენებული, ყველაფერი source კოდები დევს ღიად და საიდუმლო არ არის როგორც Linux-ების კოდები. რაც შეეხება ფასებს, ხო? აქ თვეში 10 წუთი არის უფასო. ეს არ არის გასართობი საიტი ან ასე შემდეგ, თქვენ რაღაც გამზადებული პროექტი გექნებათ უკვე, თქვენს კომპიუტერზე შეგიძლიათ ეს კოდი დაწეროთ და მერე მოსინჯოთ აი იმაზე რა ქვია, უშუალოდ საიტზე, უშუალოდ იმაზე რა ქვია, IBM კი არა და კვანტურ კომპიუტერზე ეს კოდი როგორ იმუშავებს თუ შეცდომა იქნება, ნუ 10 წუთი შეიძლება დიახ დაბა ცოტა არის, მაგრამ ნუ როგორც არის რა. ვინც ჩემს ტრენინგებს ესწრებოდით, ან პედაგოგების საყურადღებოდ ვიტყვი, რომ ეს არის ხრუბლოვანი სერვისი, რომელსაც ქვია SaaS ხო software as service. აქ პირობებია ჩამოთვლილი, ფასი აი სტუთობრივად გამოყენებაზე არის რა და ამში რაღაც $1, ნუ $1.50 საკმაოდ დიდია ჩვენთვის ალბათ ხო? თუმცა ხო, მეორენაირი პროექტი აქვს კიდევ, ამათთან შესაძლებელი არის თუ რაღაც დიდი პროექტები გაქვთ, რომელიც რაღაც $1,000,000-ზე მეტი ღირს, ასეთი და მსგავს პროექტებს ესენი იმაშობიან, რა ქვია, უფასოდ გთავაზობენ. და ნუ ქისკითი, როგორც გითხარით, ამ ნაწილში არის უფასო პროდუქტი. ისევ და ისევ მე თავს არ შეგაწყენთ და ეხლა განახლებთ როგორ შეიძლება ამ პროექტის ჩართვა, ამ პროექტში ჩართვა. უფასო სერვისი ნახოთ. ой, რაც არასწორად გავაკეთეთ ხობა. ეს არასწორად ვაკეთებ. კარგი, 2 წამით ავძებნი და ჩაგირთავთ. არ ვიცი რა წერია. კარგი. შეგვიძლია გადავიდეთ ამ გვერდზე და მე გავასწორებ ჩემთანაც. ავისრეკო.
just to keep things cleaner. So earlier, I created an account. Welcome back to Coding with Qiskit 1.
Բարեմ იყოს ეს კოდით და ესეც საინტერესო არის. ჩემზე უკეთ აგიხსნიან ალბათ. იყოს ეს ვარიანტი და
Hello, and welcome to Coding with Qiskit 1. I'm your host, Derek Wong, and I'm a research scientist at IBM Quantum in New York City. I come from a background in computational physics for material science and chemistry, and here at IBM, my job is to push the limits of today's quantum computers to simulate interesting natural systems. The point of this YouTube series is to get you up to speed with the latest developments in quantum computers for your own work. The foundation and focus will be on Qiskit 1, an open source and freely available software development kit that allows you to program useful quantum computational workflows, all the way from building quantum circuits and designing quantum algorithms to submitting them to real quantum computers and orchestrating large-scale complex workloads. As some of you may know, Qiskit has been around for 6 years already, and there have even been previous iterations of the Coding with Qiskit series. In fact, it was through the first season that I got my start in quantum computing. So it's really cool to be hosting this series now. So why are we back again? In just the past year or so, we've seen major developments in quantum computing, most notably with the onset of the utility era, where quantum computers have now reached a level of scale and reliability such that researchers can now use them as a legitimate tool for scientific exploration, as highlighted in a research Nature paper by IBM Quantum. And you can learn more about it in another video on this channel linked below. In the utility era, quantum computational workflows will only grow in scale and complexity. Already, we're seeing high-impact scientific papers that use every qubit on IBM's 127-qubit chips, thousands of gates in a circuit, and tens to hundreds of thousands of circuits in a workflow. We're seeing the proliferation of methods like circuit cutting and error mitigation that require fluid orchestration between multiple classical and quantum computers. Simply, the technology has evolved dramatically. And using these larger systems can be quite different than the 5 or 7 qubit chips we might be used to. To support this new era, we've graduated Qiskit from its development phase to version 1.0. With 1.0 onwards, we expect Qiskit to become much more stable, efficient, and a developer-ready software backbone for quantum computational workflows. And so, as described in detail in the blog post linked below, Qiskit 1.0 will specifically emphasize several new values. 1, it'll be highly performant. We've seen steady improvements over the years, but Qiskit 1.0 will be the best version yet. It'll be faster and take up less memory, making it convenient and fast to transpile circuits with 100+ qubits and thousands of gates. 2, it'll be leaner. We've removed the meta package architecture, spun off some packages like Qiskit.algorithms into a separate one, and deprecated modules like Qiskit.opflow to make it more focused and maintainable. 3, Qiskit 1.0 will be more stable. In particular, we've gone from promising bug-fixing support for 6 months in the pre-1.0 versions to 18 months of stable support without breaking changes. Feature-wise, there's a lot coming too. First, primitives in the form of sampler and estimator are now the access model for quantum hardware. This is improving upon the backend.run method that you might be familiar with from the pre-1.0 versions. Primitives will ensure that access to quantum hardware is consistent and reliable. Second, Qiskit 1.0 is ready for dynamic circuits, enabling complex logic within a quantum circuit to more efficiently generate entangled states, teleport long-range gates, and pave the path toward error correction. Finally, we're making it easy to build on Qiskit. It'll be straightforward to, for instance, build your own transpiler plugin, extend Qiskit's capabilities for your own needs, and share your code throughout the Qiskit ecosystem. We'll be highlighting all of these new aspects throughout the series, but our first stop in the next video will be to install Qiskit. This video will be useful for experienced users and newcomers alike, so be sure to check it out. In the meantime, let us know what you'd be excited to learn more about, and we'll take into account your feedback as we plan the rest of the series. Thanks for watching. Welcome back to Coding with Qiskit 1. I'm your host, Derek Wong, and this is episode 2, where we'll be installing Qiskit 1.0 and getting ready to access real quantum hardware offered by IBM. With all of these tools set in place, we'll be well on our way to running utility-scale quantum computations in later episodes. So first, let's install Qiskit 1.0, a Python-based SDK. This section is for you if you're totally new to Qiskit, and if you've installed previous versions, you should instead skip to the next section. I'll be focusing on the process for Mac since that's what I happen to have. But if your machine is working Windows or Linux, don't worry. This part is similar when installing any other Python package, and we've linked some of our favorite resources in the description below. First, we want to install Miniconda. This software manages different Python environments, which is helpful when working on different projects where you might want to have a separate Python environment for each. So we'll go over to my laptop and open a browser to start doing this. So open up a new window, and I'm just going to Google Miniconda. Here's a website that I've clicked on before. And first, I just want to talk briefly about whether you should get Anaconda versus Miniconda. They both include the Conda package, which is a commonly used Python environment manager. In this case, I happen to know exactly what packages I want to use. It's Qiskit, and I don't want a large download. So in this case, I'm going to be using Miniconda. So I'll click on the tab for Miniconda here and go into installing it. And what I'll do is scroll to the Mac OS graphical installer, since I do have Mac here, and then download the installer. When you go into this page, you'll see that they have different links corresponding to different platforms. There's Windows, there is Linux down here, but I have Mac. So you can see even within the Mac, they have different options. You can install from a bash script, or you can install using this package that corresponds to a nice graphical installer. I'm going to use the package this time. But even among this, you can see you have some choices. You have the Intel chip versus the Apple M1. In my case, to check that, I'm going to go to this button over here in the top left and click on About This Mac. You can see that I have an Intel chip right here, so I'm going to get the Intel package. Just click on that. It'll go to my Downloads folder. And let's open it up. So here I'm going to drag it onto the screen, just click through it. This is a README. Here's the license that you should read quite closely. I'm going to agree to it and install in a specific part of my disk because I just want to localize everything I'm doing for this series in a specific folder just to keep things cleaner. So earlier I created an account just for this, CWQ for Coding with Qiskit, and I made a folder called Coding with Qiskit. So I'll just put it right inside here. Continue, let it do the installation, and just wait a minute or two as this finishes up. Okay, so it's finished installing. I'm going to close out of the graphical installer, move to the trash. We don't need it anymore. And now what I'm going to do is open a window of my IDE. And this is basically an environment where I can write code, edit it, and then access the terminal. For you, you can either use Terminal and a Jupyter Notebook in your Google Chrome, but I just tend to like to use Visual Studio Code. It's free and it's pretty powerful. So the first thing I'm going to do now that I have Conda installed is to create a new environment within Conda. To do that, you need to open a terminal. So I'll just click this terminal button here. And you can see that I have Conda installed because I'm now in my base environment. But what I want to do is create a new environment so that everything I make for this project, for this series, is localized and they don't interfere with other projects I have going on. So to figure out how to do this exactly, again, I'll go back to the Conda documentation and I'm going to figure out how to create a new environment. So just Google it, look at the documentation here, and it'll tell me if I want to create an environment, I just do Conda creates -- name, and then I'll put the name of it here. So I'll just copy this code. Well, actually, I'll just type it out. Conda create name, and let's call this CWQ for Coding with Qiskit, and we'll create the environment. It'll ask if I'm sure I want to do this. Yes, and hit go. Okay, now that I've created this environment, to activate it, you can see it says right here to just activate with Conda activate CWQ. And now you can see in this leftmost part here that I'm in this new environment. The first thing I do every time I create a new Conda environment is to install pip. So I'm going to do conda install pip. Pip is basically a Python package manager within this. And so what it'll do is make sure that your Python packages are up to date, that they're compatible with each other, and that you're using stable new versions of Python packages that come out. The reason I install pip first is because I like to install packages with pip within an environment. Again, it just keeps things clean throughout the rest of my Python environments within Conda. So that's been taken care of. I've installed pip, and now what I can do is start to install Qiskit finally. So what I'll do is just type in pip install Qiskit. If you want, you could type in the particular version you want here, for example, 1.0.0. But in this case, I want the latest, most stable version. So I'm just going to do pip install Qiskit and let it install whatever version happens to be uploaded at the moment. As it's doing this, you can see that it's installing other things as well. So it's got Qiskit 1.0.2, but it's also installing NumPy, SciPy, and various other important packages for this. So again, we'll just wait a few seconds for this process to finish up. Okay, it's done. And for the purposes of this series, there's a few other packages we'll need, and so we'll just take care of them right now. And one of them will be matplotlib. This is just a package for plotting things in Python, and it'll be convenient to have this now. It'll help us visualize things like circuits and then create plots of our results. We'll also install Qiskit IBM Runtime. Qiskit is designed to be hardware agnostic. Qiskit IBM Runtime connects Qiskit to IBM's runtime environment so that you can access the 100-qubit plus devices. So I'll just type that as well here, and we'll be using this later in this tutorial. And the final thing that I'll install is this PyLatex ENC, and this will just also be part of visualizing things later on. Okay, so now this is done, we can make sure that we installed Qiskit correctly in this notebook. So we'll close out of this, and we'll create a new file that is a Jupyter notebook, and let's save it as in this folder I created already. So let's save it inside of Coding with Qiskit, and let's call it Episode 2 Installation. Now it's looking for kernels. This is basically the environment it's going to use to run whatever code I put in this Python notebook. In this case, I'm going to look for things, and there we are. There's our environment CWQ. If it doesn't show up because maybe this is the first time you're using Conda, or maybe because this is the first time you're using this particular IDE, the solution that I find works is just to shut it all down and open it up again. Sometimes that helps update things for new installations that you might have added. So I'm just going to click CWQ, and now I've loaded this particular new environment. And let's just make sure that we've installed Qiskit properly by doing import Qiskit. Oh, it requires this ipykernel package, so okay, I'll just install that right now as well. And just wait for a minute for this to finish. And there we go. We installed the package that allows us to run Jupyter notebooks in this IDE, and then it finished installing Qiskit over here. To make sure that we have the right version, we can do something simple like qiskit.__version. And that should print out the version. You can see that we are indeed on a version 1.0 or greater, 1.0.2 in this particular case. So Qiskit as a software is going to be evolving over time. I said in the first video that it should be more stable and more performant. And to follow all this progress, you can go to the GitHub. So let's go to github.com/Qiskit. And in particular, let's go to this repo right here. And you can see that this is exactly where Qiskit is coming from. This is, it tells you all the information about what it is, the installation, and some basics on creating your first quantum program. We'll do something sort of similar in later videos as well. And not only this, you can see all the code is open, and you can see all the issues being worked out, including feature requests, performance issues, bugs, pull requests that then implement these various things into the code, and all sorts of other information like the wiki and other performance metrics for Qiskit. So there you go. So we have Qiskit 1.0 installed. You know how to track its progress. And so there are some important caveats to the above if you are an existing user of Qiskit. So feel free to skip this section if you're a totally new user though. First and most importantly, Qiskit 1.0 will involve breaking changes. To install it, and only when going from Qiskit less than 1.0 to a version greater than 1.0, you will have to create an entirely new environment. Secondly, you can test if your current code uses functionality that won't be supported in Qiskit 1.0 by upgrading to Qiskit 0.46, which will emit deprecation warnings for functionality not supported in the latest versions. We strongly recommend you take this step to avoid any surprises when you do eventually upgrade. Now, regardless of whether you are an existing or new user, you should have Qiskit installed on your machine. And before we close out this video, let's also get you access to real quantum hardware so that you can test out quantum algorithms. First, you'll need to go to the IBM Quantum Platform website at quantum.ibm.com. So let me do it in this browser over here, quantum.ibm.com. Here I've already logged in, but if not, you have to create an IBM ID and then you can log in from there. And on this page, you can see all sorts of useful information. You can see, for example, this dashboard that talks about the jobs that you've had, the recent ones you've run on the various devices. There's product updates over here. And as you scroll down, you can learn there's buttons to click on the different compute resources you have to get more documentation, to search it right here, and then all of the content that's available to teach you how to use these devices. You can dig in a little bit deeper here in the compute resources tab, for example, where this is showing the resources I have access to through this particular provider. But if you can look at all the systems in this tab, and you can see that there are 11 devices that have over 100 qubits, as well as a handful that have 27 qubits over here. There's also a tab where you can look at the various jobs that you've run over time and filter through them. So going back to the dashboard, however, what we really want from here is to get our API token. This API token is how the Qiskit runtime service will identify our account with what's being run on our local Jupyter notebook. So I'm just going to copy it right here. We're going to go back to the Jupyter notebook, and we are going to now instantiate the Qiskit IBM runtime service, and this will then allow us to access the hardware. So what we'll do is we'll type in Qiskit from Qiskit IBM runtime. This is that package I said to install earlier along with Qiskit, and we're going to import Qiskit runtime service. And here what we'll do now is instantiate the service with service equals and type in the channel. Here I'm going to type in the channel IBM Quantum. You have two choices, IBM Quantum or Cloud. I should say that the IBM Cloud is likely how you'll access the hardware through the open plan, which I'll talk about more in just a second. And then from here, you're going to put in your token. So in this case, my token is what I copied before. Just paste it there. And I'll hit enter. And you should see that this now instantiates the Qiskit IBM runtime service. OK, there we go. Another thing you can do instead of instantiate it every time with this token here is to save it to your account so that anytime you open up a Jupyter notebook running on the same environment, that it automatically pulls up your details. And to do this, what you'll type is Qiskit runtime service dot save account, and you'll put in the channel here. It's the same as before, and I'm going to put in the token again and just hit enter. And so now it should be saved. And in future videos, you won't see me putting in my token again because I've saved the account to this particular environment, and I won't need to worry about that again. At this point, we're now going to try to access some hardware. And before I do that, I want to talk a bit more about the hardware that you do have access to. And so if we go back to this page, you can see, again, all of the devices that in particular I have access to through the providers that I have. But for anyone else, the question is, what can you access? Well, right now, many of the devices are equals. But in the future, we should be rolling out more herons that in general should have substantially better performance with better and faster 2-qubit gates. And you can check out the recent benchmarking paper linked below for more. To access it for free, there is an open plan. With this open plan, you get 10 minutes of QPU time per month. This is the equivalent of many thousands of shots on quantum computers with over 100 qubits each, and it should be plenty to run all of the examples that I'll be talking about in this series. There's also a premium plan where device access is $1.60 a second. So with your API key, you can now load your account to call quantum computers to execute quantum circuits directly within this Jupyter notebook. So what we'll do now here is call the backend. So now that we've instantiated this service, I can just type backend equals service.backend and then put in the name of a device. In this case, I want to say call IBM Brisbane here. So I'll type in IBM Brisbane, and it should load that backend. There we go. And now that I have this backend, I could do all sorts of things like check out its various properties here. And in particular, I'm just curious to see how many qubits it has to make sure that we have over 100 qubits. Printing out this number of qubits, we have 127 here. And so in future videos, we'll be using Qiskit 1.0 to access devices you should now also have access to. Try this out on your own. And if you have any issues in the meantime, let us know in the Qiskit Slack or the comments below. And we'll help you figure out issues in advance of our next videos of this series. Thanks so much for watching, and we'll see you next time.
და ბარემ ეხლა ვნახოთ კოლეჯები, ამერიკული კოლეჯები, სადაც შესაძლებელია პროგრამირების სწავლა, კვანტური კომპიუტერის პროგრამირების სწავლა და პლუს ჩვენს აგრეთვე ხო ეს გოგონა უკვე ოჯახის წევრი ვიტყავს. გარდა იმ სიტუაციისა, რასაც ჩვენ გთავაზობთ. ანუ ჩვენს ორგანიზაციას შეუძლია შემოგთავაზოთ მომავალი სექტემბრიდან უკვე სექტემბრის 17 სექტემბერს დაიწყება სწავლა. კვანტურ კურსზე, რომელსაც ქვია შესავალი კვანტური კომპიუტერის პროგრამირებაში. და ამ კურსის ფარგლებში თქვენ შეისწავლით კვანტური ერთწლიან კურსს გაევლით, რომელიც მოსწავლეებისთვის არის, რა თქმა უნდა, და რომელიც აკრედიტებული არის ამერიკული უნივერსიტეტების მიერ. კარგით, ეხლა მოусმინოთ.
Lanes, and I'm the North American team lead for education and Qiskit here at IBM Quantum. And through my job, I have a lot of interactions with students from all over the world. And the number one question that students never fail to ask me is, Olivia, if I want to get a job in quantum computing, what should I major in? And like most questions that exist in the world, I don't have a simple answer to that. But you can get a hint of what you might want to do for your major based on what career most appeals to you in the future. So for instance, I was a physics major in college, and then I went on to get my PhD in physics as well. And physics appealed to me because I always liked working with my hands. I was one of those people that learned by doing things and building things. And I wasn't that interested in coding. I wasn't that interested in being a software person. And I knew I wanted to be in a lab, working with devices, and building things myself. So that's a pretty good clue that you might be good at physics, engineering, and those things might interest you. I knew in the future that I would want to work in a laboratory setting, in a big team, and getting to build devices. So that was a great clue for me that I should stick to more of the engineering and the physics side of things. If you view yourself as a person who's going to work more on software or back-end or front-end development, that's a clue for you that you might want to major in computer science. Other options include math, engineering, chemistry even, and based on what career you want in the future, that can inform what degree you should be pursuing at an undergraduate level. So I generally like to break down the jobs that exist in quantum computing into 4 distinct columns. And these columns can sort of be used to sort into different majors. So the first is quantum information theory. So theorists basically work with 1 or 2 other people, not necessarily always a big team, and they get into more of the heavy math and the quantum theory behind the devices. So things that fall under quantum computing theory might be simulation of physical systems, multi-qubit gates, optimal control theory, quantum algorithms, and even error correction. And if you want to work in that domain, if any of those sort of careers appeal to you, you might want to major in physics. You're definitely going to have a strong physics background in order to understand quantum information theory, not surprisingly. The next column, which is the column that I sort of sorted myself into, is hardware or experimentalists. And these are the people that are working with the devices that are in the laboratory. Generally, they work on a bigger team. They interact with a lot of different people at the same time. and they are interested in building things, packaging things, wiring things, actually working with the dilution refrigerator, which holds the quantum computing chip. And the different jobs that fall under this category of hardware would be engineering, microfabrication, packaging, thermal engineering, working with FPGAs, circuit design, circuit layout, or microwave modeling as well. And I think if you're interested in any of these, physics again would be a really good major, or engineering. I work with a lot of electrical engineers, sometimes mechanical engineers. That is all a really, really good fit for these types of jobs as well. Next, I have the software category. So Qiskit is a software tool. If you're really, really interested in using Qiskit or working at the front end or the back end level, that might be this column. Scientific programming, if you're really interested in different software languages, if you're interested in cloud services, APIs, the user experience, algorithms, or data structures. These are all clues that you might want to major in computer science. Now, this is not what I did, but I understand that computer scientists basically take a path that doesn't have too much physics necessarily, but you can always choose to take a physics class that interests you, that might be beneficial for your career outside of your major. Nothing prevents you from doing that. And then the last column, which is sort of the miscellaneous category, would be applications. So applications in quantum computing and quantum information science basically fall into the category that I would probably more accurately label as exploration, because we don't necessarily know what all of the applications of quantum computing are going to be. Algorithms, hybrid quantum classical optimization, quantum simulators, finance, chemistry, these are all possible future applications that people are working in right now. And I think applications is a really challenging thing to pursue, because you sort of have to be a jack of all trades in order to be really successful in these types of careers. You need to know the physics, you might need to know a lot of math, computer science for sure, because a lot of what you're going to be doing is programming, working with simulators or real devices on the cloud, and you need to know how to interact with those efficiently. And then depending on the application that you're pursuing, maybe it's finance, maybe it's chemistry, you're going to need a background in that as well. So this is definitely the most open-ended category. You can major in physics, chemistry, computer science, math, many different majors would enable you to work in the applications field, I would say. So these four pillars are generally what I like to break things down into. And of course, the decision is really yours. I can't tell you what the best major is. Nobody can. You really have to be comfortable pursuing this degree for at least 4 years, but possibly even longer than that if you choose to go to graduate school, and then working in it after you graduate as well. I think sometimes when people ask me, Olivia, what is the best major to get to work in quantum computing, they want to know what jobs have the most availability. And that's also not an easy question to answer, unfortunately. There are some jobs that are open for right now for applications, software developers. There are a lot of jobs in engineering, but these trends are going to vary over time as the technology progresses. So I think the best advice that I can give anyone in this position is, you really have to follow what you're passionate about. I mean, it's cliche, but it's true. Nothing is promised to you when you graduate. Nobody says, you get this degree, you read this book, you get this job. That doesn't happen, unfortunately. So you're going to want to be able to rely on your degree, even if you don't necessarily end up working in quantum computing, to be able to get a job that still fulfills you. So that would be my advice. Sorry, there's no easy button. There's no shortcut answer, like everything in life. But I think you can really, dig deep and figure out what appeals to you the most and figure out the answer yourself.
ხო, წინა ნაწილში այս Qiskit-თან დაკავშირებით პატარა ეს ვიდეოს ჩვენება მინდოდა დამავიწყდა და ბარემ ამასაც გიჩვენებთ slideshow-ზე. აი ესეთი უნდა იყოს. ესე იგი, ეს Qiskit-ის და საიტის ინტერფეისი აქვს ნაჩვენები და აი ამ ინსტრუმენტების დახმარებით, აი ესეთი ვიზუალური ინსტრუმენტების დახმარებით შესაძლებელი არის როგორც პროგრამების წერა, ასევე სხვადასხვა ოპერაციების განხორციელება. შეიძლება ახლა ძალიან რაღაც გაუგებრად და რთულად გეჩვენებოდეთ ეს ყველაფერი, მაგრამ დამერწმუნეთ, რომ არც ისე რთული არის. კიდევ ერთხელ მინდა შეგახსენოთ, რომ ეს სიტუაციები, რასაც ახლა ინსტალაცია იმის Qiskit-ის open source-ის ინსტალაციასთან დაკავშირებით გვიყვებოდნენ, არც ისე რაღაც სასწაული რაღაცები არ არის, იმიტომ რომ ვთქვათ, ვინც Python-ზე ელემენტარულად აპროგრამებს, მათთვის ესეთი ტერმინები, როგორიც API, ეს აპლიკაციების მოდელი, BIP და ტოკენი ძალიან ნაცნობი სიტუაციები არის რა. და ეს პაკეტების მენეჯერი, როგორც სხვადასხვა პაკეტების დასაყენებლად გამოიყენება, არიქა და რაღაც სასწაული ამაში არ არის. ტოკენი კიდე ჩვეულებრივად ეს არის რაღაცა საიდუმლო კოდის ციფრების და სიმბოლოების კომბინაცია, იმისათვის რომ დარწმუნდეთ, ან ინდივიდუალურად კეთდება და ჰარვარდის უნივერსიტეტში ეს კურსებს რო გადიოდნენ ჩვენი წელს უკვე არ მოითხოვება ეს ტოკენის გენერაცია, თორედ წინა წლებში, წინა 3 წლის განმავლობაში ამ ტოკენს ჩვენ აქტიურად ვიყენებდით, მოსწავლეები მის ინსტალაციას ახდენდნენ, გენერაციას ახდენდნენ და იყენებდნენ თავიანთ პროექტებში. ჯერადად კეთდება ეს ოპერაცია. ასე რომ რაღაცა შეიძლება თავიდან ცოტა რთულად მოგეჩვენებათ ეს ყველაფერი, შეიძლება თქვათ, რომ არიქა ჩვენი მოსწავლეები ამას ვერ გააკეთებენ, მაგრამ დამერწმუნეთ, რომ თქვენი მოსწავლეები ამ ყველაფერს შეძლებენ. პლუს ამას გარდა ამ Qiskit-საც არაჩვეულებრივი ძალიან კარგი დოკუმენტაცია მოყვება. ხო და ესეთ კიდევ კურსზე, ჩვენს კურსზეც ეს IBM MIT-ის კურსი, რომელიც არის, იქ მოსწავლეები გადიან ამ ყველაფერს. კარგით. სადღაც საათი და ზუსტად 1 საათი არის, რაც ახლა ჩვენ დღეს მუშაობთ და კიდევ ერთ ვიდეო შემოგთავაზებთ ოლივიას დახმარებით და ოლივია მოგიყვებათ რა სახელმძღვანელოებს გაუწევს რეკომენდაციას და ამით დავამთავროთ დღევანდელი შეხვედრა. ოღონდ მანამდე ეს ვიდეოც უნდა ვიპოვო. სპეციალობები ნახეთ.
დღეს აღარ გავაკეთებთ პრეზენტაციას?
პრეზენტაციები ხო გქონდა?
დიახ. კარგით.
ესე იგი, ეხლა დაგვრჩა წიგნები, რა წიგნებით შეიძლება მეორე ნაწილი. ხო, პირველ ერთი ნაწილი ვნახოთ, ეს ორ ნაწილისგან შედგება, მაგრამ რო არ დავიხალოთ, საკმარისი არის. თუ მე დაგაინტერესებთ ხოლმე ეს ამ წიგნებზე ჩვენ გვაქვს წვდომა. ერთ-ერთ უნივერსიტეტს აქვს და იქაც შეიძლება თუ დაგაინტერესებთ, შესაძლებელი არის, რომ მოგაწოდოთ ეს წიგნი.
Hi, my name is Olivia Lanes. I am the North American lead for Qiskit Education and Community here at IBM Quantum. And today I'm going to be doing a book review of my favorite books in quantum computing and quantum mechanics for students of all different backgrounds. I'm going to be telling you why I think these books are the most helpful books, or they have been for me throughout my journey in quantum computing. So the first book I want to recommend is The Introduction to Classical and Quantum Computing by Thomas Wong, who is a fabulous author and a fabulous person. So this book, I think, starts out probably at one of the more introductory levels. It has a really good preface to get you started on sort of what prerequisites you might need for the book, which are minimal, and then it starts talking about what classical computing is. I really love this book because one of the things that I always complain about, and that I've spoken to Tom about before actually, is how when people talk about what quantum computing is, they always say, okay, well, you know how classical computing works. And they just assume that whoever they're talking to is intimately familiar with how classical computers process information. But I'm sure that's not really the case, and it wasn't necessarily the case for me either when I went to graduate school and I started my PhD in quantum computing. I didn't actually really know how bits worked or how even classical computers worked on a fundamental level. So he doesn't assume that knowledge. He starts talking about what classical computing is, how bits actually are used to encode different types of information, and then how classical gates are different and similar to quantum gates. So that's why I really love this textbook. It has a completely different introduction than most quantum computing books. And before he gets into, some of the harder stuff, he starts out at a place where he knows that all of his readers will be able to catch up. It also has some really good problems throughout. None of them are too difficult, so I think a freshman even can pick up this book and have a really good educational experience. All right, book number 2, Quantum Mechanics by David Griffiths. Nothing too shocking here. This is sort of the introductory textbook that basically everybody uses when they first start learning about quantum mechanics. It's a classic for a reason. It's a great textbook. Is it flawed? Yes. Is it still like the gold standard for undergrad quantum computing textbooks? Yes. So I love it because it has an interlude in the middle about what Dirac notation is and how to get started on the mathematical formalism, but it doesn't start there. It starts talking about the wave function, what the wave function is, and how do we interpret it, and what does that mean when we start talking about probability and statistical interpretations. And I think this is really, of course, the fundamental problem with quantum mechanics when we're trying to make the leap from people's understanding from classical to quantum, is that maybe people aren't as familiar with the statistical nature of reality. And so when we dive into that without explaining it, it can get a little wonky. All right, so David Griffiths, excellent textbook. Mine's a little beaten up. You can see I've written some notes throughout it, but it is well loved. You're not a physics person if you don't own a copy of this book. Third, Quantum Computer Science by Merman. This is a little bit of a different book than the ones that I have mentioned so far. This is sort of quantum computing from a computer scientist's point of view, whether these were more physics. I think at least David Griffiths is definitely a physics textbook. And this one, like I said, is more computer science. So this textbook is not going to teach you about Shor's algorithm. It's not going to teach you about Grover's algorithm or what those are or how those work. But this one is. These are really more of how to get started with the mathematical formalism. This is how do I understand what quantum computing is doing and why is it important and what is a quantum computer. He spells qubits wrong, but we can forgive him for that. He wrote a really, really great textbook. I use this a lot when I'm trying to understand different elements of Qiskit and different modules in Qiskit. And so I think that this is a really great textbook for people who are coming at it from a developer point of view. All right. Next book is Quantum Computing Since Democritus by Scott Aaronson. Scott Aaronson is really sort of a guru in our field of computer science and quantum computing. He is a professor at Texas at Austin, and he's really just such a fun and interesting guy to talk to. I've had the pleasure of meeting him on a few occasions. This is not really a textbook that you would maybe have as a textbook for a class necessarily. It's sort of broad and very wide-ranging. And in fact, there's a really great quote in the preface here that says, if you're the type of reader that only likes to digest popular science once all of the science has been washed away, skip this book. This is not for the faint of heart necessarily. This talks about, some elements that are in popular science. It talks about why quantum computing can be so powerful. It talks about, does P equal NP and why do we care? but it has some, more difficult elements as well that you really have to, spend some time with and really just sort of mull and stew in the implications of it in order to get the benefit of it. He has some great problems throughout, or he has what he says, problems for the non-lazy reader. You should do them. They're really helpful. And yeah, this is a classic. This is a great textbook. I've had this for many years, ever since I started in the field. Next is not exactly a textbook. It sort of is, but it could be. It is Circuit QED, superconducting qubits, coupled to microwave photons. These are, or they were originally lecture notes that Stephen Gervin compiled from his lectures at Yale. And this is just masterful lecture notes. I mean, it's been edited, it's been formatted in a way that, it should have a cover. It doesn't. I had to, illegally print it off the internet, but I printed the entire thing and I have kept it with all of my other textbooks on my shelves for many years. Circuit QED is basically the mathematical formalism and the physics that is behind how we actually interact with what we call transmon qubits, which are the qubits that IBM builds all of its quantum processors off of. And the physics behind it and the concept of the Josephson junction are all laid out in this textbook. Again, this is a physicsy textbook. So this is not going to talk to you about Shor's algorithm and other quantum computing algorithms and applications. This is going to talk about, how do I take a qubit and couple it to a resonator, and how do I communicate with that resonator? It's very fundamental. Good for experimentalists like me. But I never like to scare people away from understanding the experimental elements. I think it is, if not important, at least very interesting to understand quantum processors from the ground up like this. So, excellent read. It's a little hefty. There's a lot of math in it, but if you can make it through this, you're really going to understand some physics. And last but not least, we have the Bible of quantum computing. This is Nielsen and Schwang, lovingly referred to as Mike and Ike. This is the bread and butter of our field. This is a classic for a reason. This is like the 10th anniversary edition. This is the book that I used as a textbook in graduate school for the only quantum computing course I ever took. It starts at, a pretty non-technical place. It starts with, some very basic gates, and then it talks a little bit about, some of the math and like some of the decomposition that you'll need to know to understand later chapters in the book. But it really ramps up pretty quickly. It's not an easy textbook. There are problems throughout. Again, it starts off in, a pretty good place. This is definitely appropriate for a graduate level reader. Might be a little bit too advanced for an undergrad, but if you are determined, you can make it through. The problems get pretty hard and pretty complicated towards the end. But yeah, if you're gonna go into quantum computing, you're gonna have to read this book. So you might as well just buckle down and get started. All right, and there you have it. These are my picks for the best quantum computing textbooks. If I forgot any, I probably did. I haven't read every single quantum computing textbook in existence. It seems like there's a new one every other week now, but these are classics. These are excellent. If you're stocking up on your library, if you're trying to figure out where to start here. One more bonus book, The Quantum Spy by David Ignatius. This is a work of fiction, sort of. It's a thriller about quantum computing. I read it last year. It's actually a pretty good book. And if you pay attention, there are some fictional characters that are based, at least loosely, off of real players in the field. So if you're interested in that, this is a fun read. You're not going to learn too much about quantum computing by reading it. However, nothing in the book is, totally crazy and out there. It's mostly based on scientific merit. What I would read on a desert island if I had to learn quantum computing.
მოკლედ ხახო თუ კითხვები გექნება და მის ყოფილა ტელეფონი ჩართული ყოფილა მიკროფონი როგორ ჩანს თუ კითხვები გექნებათ მზად ვარ გიპასუხოთ და
მას მარტო მე და თქვენ გადავრჩით
ეს აქეთ მაგრამ ინტერნეტზე არის ხალხი ინტერნეტზე გვისმენ. უბრალოდ ჩემ ტელეფონით არის გადიოდა იქ. კარგი, მოვაჭრე ან რაღაცას ვისამთ. ჩატში შეგიძლიათ დაწეროთ, სულ ერთი დამცევა ხედოთ აბა. ეს არის ჩვენი. აი აქ ჩატში შეგიძლიათ დაწეროთ კითხვები, რამდენიმე წუთი დაგელოდებით. თუ არა და დღევანდელი შეხვედრა დავამთავროთ. მომავალში კიდევ გთავაზობთ უბრალოდ მსგავსი ღონისძიება გვექნება გაქართულებასთან დაკავშირებით მოსწავლეებს გიწვევთ ამ ღონისძიებაზეც მასწავლებლებსაც რა თქმა უნდა და ეს გაქართულების ღონისძიება ერთ-ერთი ჩემი საყვარელი პროექტია აგერ არის ეს გაქართულების პროექტი 26 მაისს გვექნება კიდევ ერთი ლაივ ჩართვები უბრალოდ რამდენიმე ჩართვა გვექნება და ეს ჩართვა გულისხმობს რომ განახებთ ქართული შრიფტი როგორ კეთდება და ქართული შრიფტის შექმნაზე გავესაუბრებით შრიფტის შექმნელებს ადამიანებს ვინც ქმნიდნენ ამ შრიფტებს პროგრამული უზრუნველყოფის შესახებ გვინდა როგორ შეიძლება Windows-ის გაქართულება მაგალითად აი აქ ჩემთან Windows-ი არის ქართულ ენაზე ნიშნავს იმას რომ ნახეთ აი საქაღალდეები აი ეს წარწერები რაღაცები არის ქართულ ენაზე იგივე სიტუაცია შესაძლებელია ხო ამ წუთას პრეზენტაციები არ მაქვს აი ნახოთ ესეც ორი წამი უნდა წესით უნდა გადავიდეს move up okay აბა ნახოთ არა ოფისიც შესაძლებელია ქართულ ენაზე იყოს ხელოვნური ინტელექტის და დღეს არაჩვეულებრივი პროექტი ჰქონდათ რაზმიკს და რაზმიკთან ერთად შეგვიძლია გავაკეთოთ ერთი ჩართვა და იგივე Linux-ის გაქართულება ან სხვა თემები, რომლებიც გაქართულებას ეხება. აგრეთვე აქ არის სხვადასხვა ისტორიები, რატომ არის მნიშვნელოვანი ქართული ენის გამოყენება, პროექტების, პროგრამული პაკეტების გაქართულება და ну, რა ვიცი 26 მაისი ვფიქრობ რომ ასე შეგვიძლია აღვნიშნოთ. სექტემბერში კიდევ გელოდებით მაღალი კლასის მოსწავლეებს კვანტური კომპიუტერის პროგრამირების კურსებზე. და წარმატებას გისურვებთ, ვისაც ეს საშუალება გექნება და სურვილი გექნებათ. რამდენად ვხედავ ახლა ერთი წამით აბა გურამ სხვა არ ექნებოდა კითხვა.
არა მას.
ოკეი.
მას სერტიფიკატები მას იქნება მას?
კი. ამ ორგანიზაციიდან კიდევ ერთხელ გეუბნებით, ეს არის კვანტის საერთაშორისო დღის ორგანიზაცია, რომელიც აღნიშნავს კვანტის საერთაშორისო დღეს და მათი ლოგოთი და ემბლემებით გამზადებული სერტიფიკატები, ელექტრონული სერტიფიკატები გადმოგეგზავნებათ ფოსტაზე და შეტყობინებებსაც მოგაწვით ამ თემასთან დაკავშირებით.
კარგით, მას დიდი მადლობა.
ხო, სერტიფიკატები იქნება მასწავლებლებისთვის, მოსწავლეებისთვის და სკოლისთვის კიდევ მადლობის წერილები. და აღნიშნული იქნება, რომ თქვენ ანუ ვინც პრეზენტაცია გააკეთა, იმ ადამიანებს რომ პრეზენტაცია გააკეთეთ. რამე გამორჩა თუ არა მე მგონი არც არაფერი. კიდევ ერთხელ კითხვებს შევხედავ, რამე კითხვა ხო არ არის, არა კითხვები აქ არ არის. წარმატებას გისურვებთ და ბედნიერ საღამოს.
ნახვამდის მასწავლებლებში და მისა.
კარგად.